Okay, hello, welcome back. We're back to stable homotopy theory, introduction to stable homotopy theory. And okay, today we're going to finish something we started last time, proving the Brown representability theorem. And then I'm going to give you some examples of spectra and some basic properties of the category of spectra. So let me state the Brown representability theorem again. So let H space be the homotopy category of pointed connected spaces, then a functor f from its opposite into set is representable if and only if it satisfies the following two conditions. So one, for every collection of pointed connected spaces, f of the wedge is product and two, for every push-out square in spaces connected. Remember, we saw last semester that there are no push-outs in general in the homotopy category, so I really need the homotopy push-out here. The map from f of y prime to f of x prime times f of x f of y is surjective. Okay, these are two conditions. Fairly straightforward. We used this theorem last time to classify all cohomology theories. And we saw that, in fact, every cohomology theory does satisfy these conditions. Okay. Is the statement of the theorem clear? Okay, unfortunately, the statement is long, so I'm not going to be able to fit it in the same page as the proof. But okay, let's prove first the easy direction. Let's suppose that f is of the form pointed homotopy classes of maps into Z, and let us show it satisfies 1 and 2. So 1 is the condition that this is one thing. That's just that's because the wedge is the coproduct, if you want, and if you want, pi 0 respects products. So the coproduct in spaces, it's also in pointed spaces, there's also coproduct in the homotopy category. That's just a basic statement about mapping spaces of pointed maps. This shouldn't be a surprise. 2 is slightly more interesting. So suppose we have our diagram like this, push-out diagram, and now let me give you a homotopy here. Now, what is, sorry, classes of maps from Y prime into Z? Well, that's well, okay, we saw what a homotopy pushout is, so it's essentially homotopy classes of like this from map X prime into Z, maps X into Z. Sorry, actually, let me write it. Let me do one more step. So it's the connected component. I'm writing map star for brevity for maps in space star. And that's just pi 0 of these pullback. That is, remember, this is a homotopy pullback. It's, if you want, homotopy classes of triples with a map f from x prime to z, g. Ooh, I need names. Let me call this I and j. G from y to z, and a homotopy k from fi to gj. All right, we saw some, I think we discussed these kind of things last semester, but do interrupt me if either if you weren't here last semester or if you are confused about what I'm saying. Just saying a homotopy pullback is given by a point here, and a path here connecting the images. And okay, and what is instead this? What is this thing? Well, this is triples of, sorry, pairs of a homotopy class of such an F, a homotopy class of such a G, such that the homotopy classes of these are equal. So you see, this map going like this is just forgetting the data of the homotopy K. And it's surjective because it's landed exactly in that situation where the homotopy exists. So the same K exists. So the map is surjective. Mapping in 2 is surjective. So you also see why we cannot ask it to be an isomorphism. This would ask that our square is a strict push out in the homotopy category, which we cannot because those guys do not exist. So we have to be a little bit more flexible and ask for subjectivity instead, which it turns out it's enough for the proof of the bar representability theorem, at least in the connected space case. It's not the case in general, as hopefully we'll be able to see in the exercise sheet if I finish write it. Okay. Is it clear? Questions? Seems not. Okay, so this was the easy direction. We had a representable functor and we saw that it satisfies the 2 necessary properties. Let's see what happens for the other direction. So now we have other direction. And we have f of set satisfying 1 and 2. The trick is going to prove something both weaker and stronger at the same time. So what we want a z and a psi in f of z inducing by Yoneda, such that the pullback of psi induces an equivalence. We're going to prove something weaker and stronger at the same time. So let me write the claim that we're going to prove. So for every x connected pointed space and for every psi in f of x, there exists an fx from x to z of x and psi tilde in f of z of x, such that, first of all, this psi tilde pulls back to psi, and second, for every n greater or equal than 1, the map f of Sn given by G sends to pullback of psi tilde is a bijection.
Excuse me, what is this ZX you wrote?
Oh, it's just a space. I'm saying that there exists an arrow from x to somewhere else, which I'm going to call zx, which depends on x.
Okay, thank you.
As I said, it's both weaker and stronger at the same time. Weaker because we are requiring this bijection only for spheres. And stronger because we are adding a new parameter here, this space x. So, okay, let's see. Yeah, let me actually show how you conclude the proof of the theorem using the claim. And then I'll go back and prove the claim. So, yeah. So now we let z be z of the point, i.e. we apply the claim for x is the point and z is the 0 in f. Well, well, f of x then by property 1 is just a point, and I'm taking z the only possible point here. Right, it's by 1. Choose this guy. And we want to claim that our f is bijective. So we want to show for every x that this map let me go, yeah, G goes to G the star of psi tilde. Remember, we have a psi tilde in f of z. we know this for when X is a sphere. And we want to prove it for all X's. So let us first show that it's surjective for every X. Show. And the idea of surjectivity and injectivity will come from applying the claim to auxiliary spaces that we built out of X. So how does this work? For surjectivity, let us consider, so let's take some eta in f of X, and we want to show that there is a G that pulls back to that. How does this work? Well, let's consider X prime is X wedge Z. Then f of X prime is f of X times f of Z, again by property 1. And so here we can take the point eta comma Z tilde. Psi tilde, sorry. Therefore, there exists some Z prime with a map, call it G prime from X prime to Z prime. And psi tilde prime in f of Z prime with the properties given in the claim. That is, it pulls back to eta comma psi tilde. And this map is a bijection. The map obtained by pulling back this psi tilde prime. And let me call this map psi tilde prime. I hope it's clear what I mean. It's the map induced by psi tilde prime under the unit embedding, but I don't want to overload the notation here. Okay, my claim is that Z prime is actually going to be Z again. Why is that? So we have a commutative diagram. And we have a map. Z goes into X prime, which remember was just X. Z goes to Z prime. And these pullbacks, pulling back psi tilde to, psi tilde prime to psi tilde by definition. Therefore, we have a commutative diagram. So we have maps, pointed maps from S to Z, going maps from F to Z prime, going to F of Sn. Now this is, by the way, pi m of Z prime, and this is pi m of Z. And this is an equivalence, and this is an equivalence by hypothesis. And therefore, by Whitehead, the map from Z to Z prime is also an equivalence. So in particular, In particular, the map x goes in x prime, which is x with z, goes to z prime equivalent to z, now is the G we seeked. That is, i.e., G upper star of xi tilde is eta. Because the class, because this is the same as G prime upper star, sorry, first inclusion upper star of G prime upper star of xi tilde prime, and that was just eta. Because that's how we defined xi tilde prime. It pulled back to eta on x and on xi tilde on z. So this map is surjective. Other questions about this? It's kind of a weird trickery. We are proving a weaker claim to a wider range of spaces, and we end up with a surjectivity claim. Injectivity works pretty much the same. So now we have fg from x to z such that f upper star of xi tilde is g upper star of xi tilde. And we want to show that f and g are homotopic. The trick at this point is to consider this diagram here, where this is the fold map, and pushing it out to some y. This again, it's a homotopy push out, if you're worried about this niceties. Then we know that f of y surjects to f of x times f of x times f of x, f of z. By property 2. And here we can take the element that corresponds to this common value, which I'm going to call, actually for brevity, I'm going to call eta, this common value, sorry. And now the idea is to apply the claim to this y. Claim to y eta, sorry, a lift, which I called it psi. Of course, there might be more than one, but I'm just picking a lift. Since this map is surjective, I can find psi, and just to be clear what this psi means, let me call this A and B. Psi has the property that A upper star of B is eta, so is a xi tilde, and B upper star of psi is eta. It might not be the only one with this property, but there is certainly at least one. So I can find a map, let me call it little h, from y to z prime, and an element, let me call it psi prime, f of z prime such that what is it? Such that h upper star of psi prime is psi, and for every n, this map psi prime given by unit eigen z prime to f of Sn is a bijection. That's again our claim. We haven't proven the claim yet. We will after we finished this injectivity proof. Okay, and the claim is again that this, okay, we want to show that this map Z goes to Y via A, goes to Z prime via H is an equivalence. Because then this will show that, well, we will give our thesis basically. And why is that? Well, again, this that again you have H a upper star of psi upper star is psi tilde. So we have a commutative diagram. Maps from Sn to Z, and that's pi m of Z going to pi m of Z prime, which is mapped from Sn to Z prime. This map, this is psi tilde going to f of Sn. This is psi prime, and these are equivalences. So this is an equivalence. But by definition, AF is homotopic to AG, because remember, this homotopy push out is the universal object carrying a homotopy of AF with AG. Therefore, HAF is homotopic to HAG, but this is equivalence. So F is homotopic to G, as we wanted to show. Again, both in injectivity and in surjectivity, the trick is the same. You build the universal guy, having the property we want, witnessing the injectivity or the surjectivity, and then show that it's equivalent to our original guy. So the original guy was already injective and surjective using the claim. So now let me go back to the claim and copy it. Paste. Okay. So are there questions about this injectivity and surjectivity proofs? No. Everyone.
Maybe one question. How hard would it be to show this without using what you called trickery? So what I mean explicitly is if you take two functors, f and f prime, that satisfy the condition of the Brown representability. So they preserves, in a certain sense, pushouts and the wedge axiom. And you have a natural transformation between them. And you know that the natural transformation is an iso on spheres. Can you in any way conclude that this is a natural isomorphism without going through this argument?
I mean, the proof of this argument, the only proof I know essentially repeats this argument in the case you described. Slightly different, but not really essential. I mean, it will follow from. I mean, it's basically doing this argument. Only one of the two functors is not representable anymore. But the idea is always you build this universal example and you use the axioms to show that you can reduce to the universal example somehow. The universal witness that these two things are the same, or the universal guide together with something ending there. You could try to look at Brown's original paper if it helps you, but the structure of the proof is basically the same. So,
thanks.
Okay. So we're going back to having to prove the claim. So we have a connected pointed space and a class there, and we want the universal guide giving you a bijection on homotopy groups, so to say, that that lifts our class. Okay. So, what's the first thing we can do? Well, first step, build G0. So I call this map, by the way, xi tilde, xi0, such that xi0 is surjective. So to speak. And there is an obvious way of doing it. Yeah. This is a very lossy kind of proof. I mean, I'm going to build huge spaces and to ensure that it will have the right homotopy type. So this is, well, we need an X to make sure that we have a lift of our Xi. And then we want something that hits every class in Sn. So for every gamma in f of Sn, m greater or equal than 1, we get we add an Sn. And so by 1, f of z is f of x times the product over all these gammas versus Sm. And so we take xi0 to be the class of xi, comma, all the possible gammas. That's a very silly thing to do on some level, but we add basically one cell. We add basically one cell to X for each class we want to hit. And xi0, we have this map. Xi0, sorry, from blank z0 into f, which is onto for all blank, n, put it the same, for every n greater or equal than 1. That's onto because, well, we put a lift by hand for each gamma. Oh, and the map, sorry, and we have a map x f0 from x to z0, which is just the inclusion of the summand. Okay, very lossy, but okay. That's okay. We want to modify it so that it's also injective, because this is not going to be injective. This is just crazy. But that's okay. Now, to fix it, we will construct a sequence of spaces. Z0 goes to Z1, 0 goes to Z2, etc. of pointed spaces. And psi I in f of Zi such that Ri upper star of, why am I calling them eta? Shouldn't, we call them psi. It's psi I. In a way that everything that is killed in f of Sn dies at some point in this sequence. And then we're going to let our Zx to be the homotopical limit of this sequence. So, how does this work? Well, let us first kill all the classes that ought to be killed. So suppose we constructed Zi, let Ki to be the kernel of this map. Sorry. And we'd like these to die. Okay. How does this work? Well, we can force it to die. So we have our Zi here. And here we can take all the classes in Ki of Sm, m greater or equal than 1. We have this map. And these maps are the maps induced by Yoneda along the gammas. And well, let's con them off because we can, so why not? And let's call this Ri plus 1. But we are not done yet. Be very careful because we're not done yet, because I haven't lifted psi I. So remember, let's look at what happens with f here. Z plus 1, f z I, go into this product over gamma of Sn, goes to 0. Well, 0, okay, the base point, whatever. These are pointed sets. So, okay, remember here we have psi I, and the point is that these get sent to the base point. Oh, no one actually interrupted me, so let me make a pause, and there is something I haven't said that people should have noticed. I said kernel here, but these are set valued functors. So what does this mean? Well, the point is that these are actually secretly pointed set valued functors, because for every x, the map from x from the point to, sorry, from x to the point induces a map from fx the point, which is the point, to f of x. And I'm going to call this image 0. Sorry, I should have noted it before. But of course, this has a canonical base point here, which is the image of f of the point. But be as it may, psi 0 goes there, gets sent to 0 here. So I have f of z I times f of this wedge of spheres times f of the point. This guy contains a class which is psi I 0. And f of zi plus 1, well, it's not equal, sorry. f of z I plus 1 is not equal to this pullback, but it suggests. Right, so I can pick psi I plus 1 that lives over this thing by 2. That we're using 2. Okay, so I have my sequence. So let me remind you, I have f of x going to f of z0, goes to f of z1, goes to f of z2, etc. And here I have psi, psi0, psi1, psi2, etc. Okay. And now we want to use it to find our zx that we desired. We're almost done. Is it clear how I went up to here? Yeah, okay. So now the idea is I get z to be the colimit of the zi's. So, okay, so far so good. And I need to lift psi though. And this is something I actually forgot to tell you, unfortunately, but the point is that you can write z.
Excuse me, Denis.
Yes?
I'm just very confused with the directions of the arrows in this sequence
Oh,
that you
you're
wrote.
right, you're right, you're right, you're right. You
Okay,
are
thanks.
absolutely right. These go in the other direction. Thank you, Joachim. F is contravariant. And of course, psi I plus 1 gets sent to psi I. So this is and actually, now that I'm thinking about it, I actually don't need that z is the colimit of this zi. I can just also define it as this push out if you don't want to use the formula. It doesn't really matter. Where this map actually, let me be precise, this map comes from the inclusion of zi into zi plus 1. It's just a wedge of all these ri's. Yeah, we don't need it, it's the colimit actually. It's a good intuition that it's the colimit, but it's not actually needed in this proof. So even if we didn't know this formula, it is still working. And so you have f of z subjects in this product f z I plus 1. Oh, sorry. No. I'm writing the wrong push out. Let me actually. Sorry again. Sorry. That's actually silly what I wrote. I wrote something that works in an additive context, but not in a non-additive context where we are. So here you have to be a bit more careful. Here you have the wedge of the even guys and the wedge of the odd guys. And you can always send zi to z2i and zi to z2i plus 1. And you want to say they are the same. Okay, now it's much better. Okay. Yes, okay, now it works. Sorry for this misindexing. Okay, is it clear? Sorry for the mistake, I hope. Also, can you read the color I'm using actually? Yeah, okay, good. So here you can take a class xi2i class xi2i plus 1, and this is indeed pulling back. In the pullback, this coincide with xi, so it's fine. It's actually well defined, and by 2, we can find finally our xi tilde in Z. Oh, I guess I should call this Zx, since that's what we call it in the claim. Okay. Okay, now I just need to show you that this Zx has the properties that we wanted to have. So we have a map.
Could you say a few words about why do you divide by this odd and even parts in the pullback?
It's secretly just that I get the colimits. I want to identify, I want something where xi I is identified with xi I plus 1. And this work, if you identify xi2i with xi2i plus 1, then this glue together nicely. It's
Okay,
just,
thank
you
you.
can try to do it for sets, for example, for pointed sets, and see what happens with this push out. And you'll see that it's just a trick to reduce this sequential colimit to a push out where we have control by property 2. So we have this map, and we know it is surjective because there is this map. This map was surjective by construction. So the only question is this actually injective? So let's G from Sm to Zx such that okay, that's G prime such that G upper star of xi tilde is the same as G prime upper star of xi tilde. And I want to show that G prime factor through some Zi. And this is, this is slightly yeah. So actually, first let's simplify. And remember, G and G prime are actually elements in pi m of Zx. So I can just take G times G prime inverse. That's a group, so we're allowed to it. We're allowed to do it. And this is what's called G double prime, and one can show G double prime upper star of psi tilde is 0. That point 0 that I described. And so up to replacing G with G double prime, G prime with G double prime, I can assume G prime is this constant map at the base point. That's just, this is just actually, let me spell it out, this follows from property 1. You use property 1 really? Yeah. You use the fact that f of Sm wedge Sm is f of Sm times Sm. And you write the, what does it mean to have the composition. And you see that. So, okay. Now, now I claim that pi m of zx is just a colimit over I of pi m of zi. Let's see. The quick way of seeing this, well, it's identifying Zx as that homotopy colimit. I should have thought about this better. But... So this push out. Well, okay. The easy way to show this is to show that actually the homology is the colimit of the homology. And this is easy because the homology behaves properly with push-outs and use Fourier-Witz, relative Fourier-Witz. I don't know if people remember it, we did at the very last end of last semester, the relative Fourier-Witz theorem, that the map on relative homology to the relative homotopy groups is 0. So since, yeah, so that's, at the point is, the upshot is that G lifts to some Zi. If you want, this is a compactness argument. This is morally telling you that Zx is a mapping telescope. Okay, once you have that G lifts to some Zi, then you won, because G upper star of psi I is 0 by definition of G, by our assumption. And so Ri composed with G is null homotopic, because in the construction in Z I plus 1 we killed all these G's. We added a cell that kills all these G's. And so we are done, finally, with the claim. Sorry about this colimit thing. I clearly hadn't thought this through. What was the elementary reason for that? And the point is that you want to identify this homotopy push out with a mapping telescope. Okay, and this ends the proof of Brown representability. And a very important theorem it is. And okay, I'll show a couple of consequences now that I think will be interesting already on their own. But first, are there questions about this proof? Okay. As a corollary, I'll give you, it's more of a corollary of the discussion we did last time, but it follows essentially from the Brown representability. So if A is an abelian group, there is a natural isomorphism H tilde, actually H, okay, let's say H tilde of X pointed homotopy classes of maps where K, A, comma, N is the Allenby-MacLane space. Which is a pointed space with the property. A pointed space with the property that this is 0 for I different from N. Ooh, sorry, it's supposed to be N. Yeah, for I equals to N. So actually this corollary also shows that that there is only one such Allenby-MacLane space, and I'll explain how this works now. So proof, well, we know that H and tilde satisfies the hypothesis of Brown representability, or more precisely, it's representable even in non-connected pointed spaces. We did a discussion last time using a trick with H tilde of the suspension to reduce to the case of connected spaces. So there exists a space KAN representing it. And now let us show that it has the homotopy groups that we want. Pi I KAN is just H tilde I of, sorry, yes, let me say it explicitly as SI from KAN pointed, and that's just HI of, HN tilde of SI, which is indeed 0 if I is different than N, and A if I is N. So KAN is indeed such a pointed space. And now I want to show actually that there is only such one space. So let K be another space with this property. Then by Hurewicz, H and tilde. Ooh. No one interrupted me. Come on, people. Didn't you realize that there was a missing A on the left-hand side, that A was only on the right-hand side of this thing? Ah, okay. Sorry, I'm going perhaps a bit fast if you don't notice these missing things. Because, of course, the right-hand side depends on A and the left-hand side didn't, the way I wrote it, which, well, would have been interesting at the very least. So, anyway, Hn kz is A. And so by the universal coefficient theorem, Hn ka is just going to be hom AA. Oh, sorry, we also need H tilde I kz is 0 for I less than n. That's still by Rivets. Because if you remember, H tilde n ka is given by, it has an hom term and an x term, and the x term vanishes by the, so it's hom. And now this is maps from k to kin, kan. And so now we take f from k to kan corresponding to id a and hom aa, and this gives an iso on homotopy groups. Because it gives an iso on Hn tilde by Hurewicz. Iso on Hn tilde implies iso on pi n, and there are just no other homotopy groups to be checked. And so it is an equivalence. In fact, we found a canonical equivalence. We show that there is exactly one map, one homotopy classes of map from K to KAN that is the identity on pi n. Okay, this is a theorem that's usually proven in a very different way in elementary classes, but since we have it from, we have the Brown representability theorem now, we are allowed to play it cooler. So as an example that you might already have seen, S1 is just a KZ1 because it has that property. And so H1 tilde x comma z is equivalent to the homotopy classes from X to S1. And actually, another example, by applying the corollary to X plus instead, you get that Hn x comma a, which is Hn tilde of x plus comma a, x plus kan pointed, which is just homotopy classes from X to KAN, where X plus is just X, disjoint union of base point. Let me write it bigger here. That's actually the way the theorem is more often stated. But that's a completely equivalent. And so that's this interesting fact. In fact, one can show that homotopy classes from X to S1 are the same thing as isomorphism classes of line bundles. And I think we will discuss it perhaps in a couple of weeks when we talk about topological K-theory. And so you can see that every line bundle is determined by a cohomology class, surprisingly enough. It's what's called this first Chern class. But okay, if you have never seen what a line bundle is, don't worry. It's just a fun example at this point of what you can get. Thanks it. Yeah. Okay. Questions so far? And if there are no questions, I'll give a couple of examples of spectra, and then we'll consider the lecture over. Okay, examples of spectra. So let me write as a title. Remember, a spectrum was a sequence En and equivalences of En with the loop of the next guy, what we call typically a de-looping. And the first guy I want to give is HA, the Eilenberg-MacLane spectrum, where A is an abelian group. Well, okay, let me do greater or equal than 0. It's just a point when n is negative. So because, you know, negative cohomology is trivial, so it's represented by the point. So let me, and this is this canonical equivalence that we just constructed, since this has pi n is A and 0 other degrees. Or if you want, set it differently, this is IE. It is the spectrum corresponding to H tilde star A, to this cohomology theory. The only cohomology theory we have. So it has better have a spectrum. And that's a very important spectrum. In fact, and we will see it, I think, next week or perhaps the week after, this gives a fully faithful functor H from abelian groups to spectra. So you can embed abelian groups into spectra. And one way of thinking about spectra is as sort of a generalization of abelian groups as coefficients of your cohomology theories, where the cohomology theory is not just coefficients in abelian groups, it has coefficients in fancier things. And okay, and just because it is a very important one, let me denote a very special guy, which is the zero spectrum, which is, if you want, the Eilenberg-MacLane spectrum of the zero group, which is just, you know, points everywhere. It's a stupid spectrum if you want, but as the 0 billion group shows up very often, so does the 0 spectrum shows up very often in the discussion. So I think I should mention it at the very least. Okay. The next example will be more interesting.
Question, so does this embed fully faithful into the infinity category of spectra or like the homotopy category?
No, in the infinity category of spectra.
Oh, okay, so there are no
you are confused because the mapping spectrum will have negative homotopy groups, but this doesn't involve for a full faithful embedding.
Okay, thanks.
It's a statement that there are no negative X groups in the derived categories. But okay, let's not overstate it. We will see it as a consequence of a much more general theorem, the recognition theorem, which is going to be the first major theorem we will cover in this class, and will be the next topic as soon as we finish giving examples of spectra.
Excuse me. You just said that this H is then into the infinity category of spectra.
Yes.
So, do we take a billion groups then with like a trivial infinity category?
Oh yeah. I mean, okay. Let me, for the last time, I'm going to put a nerve. When I took up a one category as an infinity category, I silently insert a nerve. Because a nerve is, as it will be an exercise in the exercise sheet, is actually fully faithful embedding inside infinity categories. So you really don't lose anything.
Okay, thank you.
No, but okay, if you want, I mean that the mapping space between two element McLean spectra is discrete and given by the Helm set, or homotopy equivalent to the Helm set of the corresponding abelian groups. So I haven't proved it yet. We will, but as a consequence. Okay. Okay. Let me give you another definition, which I don't remember if I gave it last time or not. We have a functor omega infinity from spectra to pointed spaces. We just send En plus 1 to E0, the zeroth space of the spectrum. And yeah. What to say about it? Let me give you just a silly example for now. Omega infinity of HA is just A pointed by the identity, by the zero element as a set. Since it's the only example of spectra we have so far, we have this thing. And you can think of omega infinity as somehow the underlying space of the spectrum. Unfortunately, a spectrum is not just a space with some structure. It has more stuff, more information included in the negative part, which I don't think we can talk about today, but we will see. We will devote the next couple of weeks about seeing exactly in which sense omega infinity is the underlying space of the spectrum. So.
Excuse me? Maybe I missed, but does this omega infinity thingy have a name?
Zeroth space.
Oh, the name is the zero space.
Yes.
All right.
Yeah, sorry. But people normally call it the omega infinity, to be honest, in practice. But okay. And sometimes you can hear people calling it the underlying space, even if it's not really an underlying space. Just
Thanks.
intuition. Okay. Why am I introducing omega infinity when I promised you examples? Because omega infinity has a left adjoint, which is sort of like the free space on the spectrum. Sorry, the free spectrum on the space. So omega infinity has a left adjoint. Sigma infinity goes from space, from star and spectra, and that's the example I want to discuss now, this kind of spectra here. So if X is a pointed space, we can build what's called Q of X, is the colimit of the following diagram. So I have X, and this goes omega sigma X by the co-unit, by the unit, sorry, of the adjunction, and you can iterate this omega sigma square of X at infinity. And for reasons that will become clear, well, okay, this is clear why I want to call this, but the notation is going to be rigged. So this is going to be something you prove, not something you define as notation. And this space here is also a pointed space, has the property that pi n of qx is the same as the stable pi n of x. If you remember, stable pi n of x was defined as the colimit over n of pi n plus n sigma n of x. We defined it at the very end of last class, I think, because by the Freudenthal suspension theorem, when x is connected, when x is a finite space, I think this ends up being, this stabilizes. Sorry, now when x is any space, sorry, this colimit is constant after a while for every n, and so it gets more and more. The n that you need for this diagram to be constant is to be bigger, but that's just the colimit over n of pi n of omega m sigma m. And then pi n commutes with filter colimits, so this is exactly the colimit of this space. So this is a very classical object, and it's a space whose homotopy groups are the stable homotopy groups of X. And this has a map from X, of course. In particular, notice that you have omega q of sigma x is equivalent to q of x, just because how we build things. Because this is equivalent actually as omega colimit over m omega m sigma x, but omega commutes with filter colimits. This is an important property that I think maybe I should have emphasized this before. In pointed spaces, pullbacks, homotopy pullbacks commute with filter colimits, or sequential colimits in this case. So you can move it inside. And that's just qx. So I have a natural equivalence like that. So we can build a spectrum. Sigma infinity x, whose nth space is going to be q of sigma n x. And together with these natural equivalences that I just discussed.
Maybe one question to the co-limit above. What is the map from omega sigma x to the next thing? Is this just a unit and sort of omega and sigma commute in some way?
No,
or
no. It's omega of the unit for sigma x. It is omega of the unit for sigma x. The unit for sigma x gives a map from sigma x to omega sigma square x. Right? Omega sigma x.
Yeah.
And then you can apply omega.
Thanks.
Now, there is no commutativity between omega and sigma. That's very important. You're not allowed to move them around. So you have to be very careful that they stay well separated, each on its space. And this is, for example, the next one is omega square of the unit for sigma square of x. And so on and so forth.
Excuse me. Could you maybe put a reference for this homotopy
Yes.
pole breaks commute with filtered columns?
Yes. It
the
is. I am almost writing that section in the notes, and there will be a reference for it. I'm sorry for how long is it going to take to write this note. It's just very exhausting, but it is. Well, okay, it's a special case actually, the descent statement I wanted to state the last time, but I didn't, so that's probably not a good enough reference, so I'm going to.
Okay, thank you.
And I want to insist that this is true often, but not always. This is true in general for compactly generated infinity categories. It's the right setup where this happens. But okay, let me not enter into the technicalities. That's not very important. Just it's something that happens that you should expect, but it shouldn't also be surprised if it doesn't happen in the place you're working with. Exactly as in ordinary categories, you can check that pullbacks do commute with filter colimits in sets and in abelian groups and in many other places, but it does not in topological spaces, for example. Which is very annoying, but what can we do? Okay. Okay, do I have the time to do the... Yeah, I think I have the time to do the following lemma. So let X be a pointed space and E a spectrum, and thus a natural equivalence between maps in spectra from sigma infinity X to E and maps in pointed spaces from X to omega infinity of E. Now, this giving a map from sigma infinity X to a spectrum E is the same thing as giving a map from X to the underlying space or the zeroth space of E. And okay, let me put the proof here. And how does the proof work? Well, we can write maps on spectra, remember, is the same thing as the limit over n of maps in pointed spaces of the nth space of the spectra. This was basically by definition of the infinity category of spectra. We define maps of spectra as this homotopy limit, which it is by definition of sigma n. Now this is maps in pointed spaces of Q sigma n of X E n. And now And now I have to put in Q, which I have limits of maps in spaces, pointed spaces, or a co-limit omega m sigma m x en. And so putting it out, I have limits over m maps in pointed spaces omega n sigma m plus m en. And yeah, okay, that's the thing. It's just unwrapping all the definitions until they become. And let me write this diagram now. Let me actually draw this diagram. So limit and maps are going to be maps in pointed spaces. So we have a map, sigma n x. I'm going to have a column like this. And that's just the co-limit computing Q0. But then Q of x, but now we end up with Q of sigma x, and that's these maps. These maps are just obtained by taking loops, using the fact that loops of E1 is E0 and loops of sigma x is loop sigma x. Sorry, omega sigma square x E1, etc. And then you go on, and here you get a map. Let me write a sigma 2x E2, etc. And you take the limit of this diagram. But the point is that you can take the limit of this cofinal diagram diagonal here. Co-initial, sorry, I should say co-initial. Because every element in this poset is dominated by an element in this subposet. So you can just get that. And the point is that here, these are just equivalences given by the loop sigma adjunction, if you what these maps are. And this is, of course, just maps x to omega infinity of E by definition. So we can take the limit over the constant diagonal diagram. Okay. And so we have what we wanted to have. And you can actually write very explicitly what this equivalence is between maps sigma infinity E to maps x to omega infinity. It's very concrete and very explicit. And okay, I think I'm already over time, so I'll stop here. I just want to say that this proof is very short, very easy, very everything. It took me 2 days to get the diagram right. I kept getting confused about which arrow went in which direction, and so don't be too worried if I'm presenting it in a very neat and clean fashion here, but it took some work actually to straighten things up. Although even if the statement after you play with it a little bit, it's obvious, it's still some work to understand where the arrows go. Okay. Questions?
Yeah, I think I got one. So it seems that somehow this adjunction between sigma infinity and loops infinity is somehow the key thing that we want to get, and somehow we need to put this Q in so that we get it right. And you put the Q into the sigma infinity construction. Could we have equally as well put it in the loops infinity construction?
No, because the Q is there to make sure that sigma infinity is actually a spectrum as I defined it.
I forgot how you defined it. You defined it
A sequence of
as
spaces
omega
such
spectra?
that, yeah, for me, spectra
okay.
is omega spectra. I am
Okay.
trying to, and as I said several times, there are different terminologies in the literature. Unfortunately, that's rather unfortunate, but I'm choosing one that should make read the literature, the relatively modern literature, easy. And the terminology that I feel is going to be the one standard from now on, because I think that's probably the thing that's more useful for you. There is also a notion of a spectrum that is what I would call pre-spectrum. And
if you would have taken this as the definition, then we could have done it the other way around.
I mean, I would have to define you what the infinity category of pre-spectra is, which is more annoying actually, because it's a lax limit, not just a limit. So you have to play a little bit with coherences. And I actually thought of doing it actually, because the spectrification factor is sometimes useful, but in the end, in the interest of time, I decided to not do it.
Okay, thank you.
And this also allows me to define the omega infinity as literally the zero space, like here. This choice simplifies the matters. If I work with pre-spectra, I would have to do a more complicated construction reminiscent of this Q.
Yeah, but then sigma infinity would be easier, right? So it's kind of a trade-off, or not?
Well, the point is that this sigma infinity that I defined and this omega infinity are the ones that are going to matter in the following, and for pretty much everything you're doing. I'm not that interested that the name sigma infinity corresponds literally to the definition, as much as that the functor sigma infinity is going to be the right functor that we want to use in what's going in the future. For example, the homotopy groups of sigma infinity has to be the stable homotopy groups of my space. That's only one of the reasons why I like this sigma infinity. And also when you read, let's say I made this choice to stick up with this terminology. There are other possible choices, but I think this is the simplest one and the one that's going to cause less possible confusion. And yeah, there is a very amusing note by Thomas Nikolaus and Achim Krause about groups for homotopy theorists, about what would happen if the theory of groups were developed along the lines that you are suggesting for the theory of spectra. And it's very fun to read and also very unnatural, which is their point, of course, in writing it, to show that while you could take that approach of always carrying out a presentation with you, so to speak, it's actually, well, in the case of groups, it's obviously a crazy thing to do. So their contention is that for spectra, it's also not perhaps the best choice. And, well, okay, it's a bit technical to read actually, which is part of the point. But if you find it and read it for a little bit, you'll see what their point is, I guess. Other questions?
Maybe I have another question. So out of every spectra, we get also a cohomology theory, right?
Yes, we get a cohomology theory. We also get a homology theory, which I'm going to define very quickly next time. I think we need just another ingredient and I can give you a homology theory, but yes.
So we get for every space in particular cohomology theory. Are there easy examples where one can write down what this is explicitly?
There is only one that I know, actually. If you take X to be S0, and the spectrum sigma infinity S0 is what's called the sphere spectrum. It's a very important spectrum. Its homotopy groups are the stable homotopy groups of spheres. Then the corresponding cohomology theory is called stable cohomotopy. And it's well, pi up S comma upper star of a space Y is how was it defined in elementary terms, actually? Well, okay, I don't remember the definition off the top of my head. It's kind of fiddly and it boils down to whatever is represented by the sphere spectrum. Oh no, now I remember it. It's maps from, it's the colimit. This works when I is a finite CW, sorry. From sigma n Sn. I mean, of course, secretly this is maps from Y to QS naught, which is, of course, the definition that we would like to take. Oof. Plus. And it's that's the only one that I know that has even a name. Is it interesting? I guess so. It's a universal one. It's the initial one in some sense. It's also horribly hard to compute. So spectra have these double lives that we have only seen in part. One as generalization of cohomology theories, or things representing cohomology theories, and another one as things representing, generalizing abelian groups, which is, I would actually contend, is their more important aspect, but we haven't been able to explore it properly yet. That's the next topic that we're going to cover. And sigma infinity is more like connected to this second aspect. But they intermingle in fun ways, and it's just part of their power, I guess. Okay, other questions? Then I'll stop the recording and see you on Monday for more properties of spectra. And unfortunately, no more examples, but that's life sometimes.
Excuse me?
Yes?
I just wanted to say again that the intuition you give in this lecture is always really funny, but the lecture today was again too fast for us.
Too fast. Okay. I'll try to go slower next time then.
Okay, thank you.
Okay. Okay.